Hello and welcome to the first part of integrating external tools in Sliver, the 20th video as part of our Red Team Fundamentals mini-series. If you have watched our video on Sliver's Armory, you will have seen that Sliver provides the ability to execute third-party tools with relative ease. All you have to do is install it from the Armory and away we go. Although this is excellent and the Armory provides an abundance of tools we can leverage in our assessments, there will be times when we also want to bring our own. Now there are several methods of doing so, and in this video we will explore the approach using the execute assembly command. As always, everything we teach in this video is purely for educational purposes. We accept no responsibility for your actions. One of the most fundamental skills of any red team operator is being able to leverage tooling in order to achieve certain tasks. This could include enumerating some information or even exploiting some memory-based vulnerability. Whatever the case, whilst many actions can be performed manually, such manual execution is both time-consuming and prone to errors. Any mistyped command leaves behind another artifact for the blue team to detect. Instead, we can write our own tools or leverage third-party tooling to achieve our objectives. Whilst we won't delve into writing custom tools of our own, we will shortly examine how we can leverage pre-existing ones. Now, it is important to note that the execute assembly command only works with .NET assemblies due to .NET's Common Language Runtime, or CLR. The sideload command can assist us in running any standard portable executable. However, we will discuss that in the next video. As such, before we proceed, let's take a look at how we can set up an environment in which we can compile such assemblies before we take a look at the inner workings of the execute assembly command. Now, before we continue to install a compiler, just one thing I want to note is that I've set up a fresh Windows 11 VM. Additionally, I have also disabled Microsoft Defender, as when you are compiling tools, it is good to do so, as otherwise every time you compile your tool, it will most likely be flagged by Defender and thus quarantined. So as you can see here, real-time protection is disabled, some other settings, automatic sample submission, and for safety precautions, I've also added the C drive as an exclusion. And what this will do is any subfolder within the C drive will be automatically excluded from scanning, because I still find that even if you disable real-time protection and these other settings, Microsoft Defender still somehow manages to flag certain files. So this is a good safety measure. Now, to disable Defender so that it doesn't automatically start every time you boot up your system, you're going to want to go to your local group policy editor, navigate to administrative templates, Windows components, and then scroll down here a little until you find Microsoft Defender antivirus. One of the first things you're going to want to, enable is the turn off real-time protection setting. So as you can see here, it's in the state of enabled. And when you do so, you're going to want to reboot your system. And once that's done, you're going to want to go to the parent folder of Microsoft Defender Antivirus and do the same for the turn off Microsoft Defender antivirus setting. And then once you reboot once more, Microsoft Defender should be automatically disabled. Now, for some reason, it is really hard to disable Microsoft Defender antivirus from Windows. I'm not sure why. But Microsoft just doesn't make it an easy option. Now, as for the compiler, there are several different ways you can install a compiler, but by far the easiest method is by using Visual Studio. Now, Visual Studio supports workloads, which are essentially bundled up packages that provide a development framework for a particular programming language. Now, for the most part, every offensive tool that we compile and execute through Sliver's execute assembly command will be built using .NET. And Visual Studio essentially provides everything we need to get started. So let's just select free download for the community version. And once downloaded, we can run it. The UAC prompt will open up, we'll select yes, and then Visual Studio will proceed to unpack. Now, before we can install any workload, we'll just let Visual Studio installer pre-configure itself and simply select the continue button. Now, once installed, you'll be presented with Visual Studio's supported workloads, and you can actually install all of the individual components by their own by going into the individual components section here and installing any individual component that you require. You can also install language packs and specify the installation location if you want as well. But in our case, what we want is the .NET desktop development workload. And once selected, you'll see that Visual Studio selects several required packages for that workload, and then several optional packages as well. And you can enable them or disable them as you please. In our case, I'm going to disable GitHub Copilot because I'm not really much of a fan of AI programming. And once selected, you can just hit install. And this can take a while, so just give it some time as there's a lot of things it needs to unpack. Now, for the first time you launch it, you'll be prompted to log in with an account. We can skip this, and then you want to configure your development settings. So you can just leave it as general, then choose whichever theme you want. And from here, just simply run the Start Visual Studio button. Now from here, you'll be able to create a new project, open up an existing project, or in our case, and in most cases when you will be compiling third-party tools, you can just select the Clone a Repository option. And what this will do is it will ask for a repository link of the tool that you want to compile, and then you can immediately clone it. Now you'll see here the cloning proceeds. And in some cases, you'll be asked to update the .NET framework version. Now this is important because some tools will be built on a different .NET framework version. And in order to compile them, we will need to compile them against that specific version. So in this case, it is asking us to update to .NET Framework version 4.8. So I'll just select that, select remember my choice for this operation and continue. Now, once done so, in the Solution Explorer, you will find all of the tools source files. So for instance, taking the Seatbelt source code file, we can scroll down here, remove stuff that we don't want. For instance, the print logo function. And as you can see here, editing the specific tool becomes a lot easier. And this is the benefit of having an IDE because everything is packaged all into a single environment. Now, whenever we want to compile the tool, we can use build and then the build solution option. And what this will do is it will build the entire solution into a single executable ready for use. But before we do so, you might want to change to the release configuration. Now, the primary differences between the debug and the release configuration is that debug will contain a lot of debugging information capabilities, and it's really just more useful when you are debugging a particular application. But to reduce the content that is packaged within our executable, we will want to select the release configuration, as the release configuration will only contain the compiled source code. Now you can also change the CPU you compile for. In this case, I will leave it as any CPU, but if you go into the configuration manager, you can actually select a new CPU depending on the specific architecture of the endpoint on which you are running your tool. And with that, we can build a solution. And then you'll see here in the output column at the bottom here, you'll get some information about the build. In this case, the build succeeded and we get a path to its executable. So I'll just open up the File Explorer, navigate to the path, and you'll see here that the executable is present. Now to confirm everything is working, I'm going to open up the terminal, and from here I'm going to run Seatbelt, which should print out its help menu, in which case it does. And from here we can upload the tool to our local client instance, and from there we will be able to run the execute assembly command. Sliver's execute assembly command can take in any .NET compiled assembly and execute it entirely in memory without ever touching the disk. And from an OPSEC perspective, this is highly valuable, as many antivirus and EDR solutions primarily scan for files on disk. Furthermore, because RAM is volatile, meaning it can change suddenly and unexpectedly, its contents are lost when the system is shut down or rebooted. As such, this leaves minimal forensic artifacts, making our operations more stealthy. Naturally, you may wonder how this is all achieved. Sliver achieves this via the implementation of a tool called Donut, which is a position-independent code loader capable of generating shellcode for execution. Now, the nature of position-independent code, as opposed to position-dependent code, enables Donut-generated shellcode to be loaded at any location in memory. As such, when running the execute assembly command, Sliver 1 takes in a .NET assembly, 2 performs the conversion of assembly to shellcode via a library named GoDonut, 3, it creates a sacrificial process and loads a DLL, which hosts the common language runtime environment, which is necessary for executing the assembly shellcode. And we can actually inject into the current implant process rather than creating a sacrificial one, but the sacrificial process is the default behavior. We will take a look at why this may be important shortly. And 4, it copies the assembly shellcode into the process and initiates a new thread at the loaded DLL's entry point, which then loads and executes the .NET assembly in memory. Now, I know this can all be a little bit confusing, so I'm just going to run the execute assembly command with the Seatbelt tool, and then I'm going to provide an argument here of group equals all. And what this will do is it will run all of the checks that Seatbelt performs. Now, we will get into Seatbelt later in this course, but what this should do is launch a sacrificial process for a decent amount of time, which will allow us to inspect what is actually happening. So let's execute this. And if we go back into our client system, you'll see that notepad.exe, which is the configured process that launches as a sacrificial process, launches as a child process of our implant process. A lot of processes there to unpack. But if you've also just observed, the process has terminated. And this is the behavior of execute assembly. It launches that sacrificial process, performs what it needs to perform, and then terminates that sacrificial process. And if we take a look at the command line output of execute assembly, you'll see here that we get very much of the same output that we received when we tested whether the tool is working. However, the main thing that I want to show you here is the .NET assembly section. As you can see here, currently there's nothing to display as the process has terminated. So what I'm going to do is I'm just going to run this again. And if we now go into the .NET assemblies section here, and if you take a look at the structure, you'll see that we have several app domains. Now, an app domain is essentially an isolated environment within a process where modules and applications can execute. So you see here we have several different modules that are loaded, but one of these modules is named Seatbelt. And this is our application essentially being loaded within the notepad.exe process. And once loaded, our application executes and therefore can perform all of the enumeration that Seatbelt performs. Now, interestingly, if we select some of these columns here, there's one specific column called the native image path. And if we select this, add this to the active column set, you'll see here, once we scroll down, the Seatbelt application does not have a native image path. Now, a native image path essentially specifies the location of where the specific application or module resides. Now, as you can see here, this value is empty, both for the file name and for the image path. And this is because the Seatbelt application is launched entirely in memory. And this is the benefit of using execute assembly. Now, just to finish up on the point of .NET assemblies, because they depend on the CLR, only when the CLR is loaded can .NET assemblies be executed, as the CLR provides .NET assemblies with an environment for interpreting and running code. Oh, and by the way, if you have never heard of what a sacrificial process is, in its simplest form, it is a newly launched process that serves as a launchpad for running commands independently of the Sliver process. Because every process has its own memory space, a sacrificial process has no tight connections to any other process on the system, which makes it ideal for use as a dummy for all necessary injection tasks. So with that understood, let's now take a look at how we can leverage the execute assembly command. Now then, running execute assembly is rather straightforward, and all that we need to provide is the command with the local path to an assembly we want to execute, and then additionally any arguments that we want to pass to that assembly. Now, execute assembly is very rich in its capabilities. As you can see, it supports several different switches for the evasion of several different Windows-based security implementations. You can also perform things like process ID spoofing. You can change the process that is being injected to. That is, change the sacrificial process that is being launched, and then several other command line switches that I recommend you explore. However, at its most fundamental, as you can see here, we provide the name of the tool we are running and then its arguments. And once executed here, the assembly should execute, and give it some time, it should provide us with the output. So as you can see here, we can see much of that same information that we gained earlier, gaining a better understanding of the operating system that we are examining. And again, we'll get into the Seatbelt tool a little bit later in this mini course. Now, there is one issue with execute assembly, and that issue is that the command line arguments that we supply for execute assembly is limited to a maximum of 256 characters at a time. Now, if we supply anything more than 256 characters, you'll see here that we get a warning message. And all that this warning message is indicating that in order to be able to execute any commands that exceed this limit, we need to execute in process instead. So rather than creating a sacrificial process, injecting into the implant's current process. Now, before doing so, there are several considerations we need to take. One, do we have a backup implant should the primary implant crash? And thus it is important to have a backup. And then also, could the implant crashing affect any surrounding components of the system? That is, more specifically, does any system component rely upon the implant? Now, if these two considerations can be met, we can simply proceed with the Y character. And once executed here, instead of, again, creating that sacrificial process, it will inject the assembly shellcode within its own process. So let's just observe this once more. I'll provide the I switch and then the arguments of group equals all. If we go back into our client system, actually you'll observe that the parent process of our Sliver implant crashes. And this is why it is important to take those considerations into account, because injecting large shellcode into the Sliver's implant process is very fragile, and as you saw there, the implant crashed. And if we did not have a backup implant, that would have meant we lost our entire session. And you'll see here by running the sessions command, the implant is in a terminated state. So to summarize, try to limit all of your command line arguments when running a specific tool through execute assembly. However, if this is not possible and you are injecting into the implant's current process, just remember to take into the consideration those two key points we mentioned earlier. And that concludes our operation of integrating external tools in Sliver. I hope you found this video informative. In the next installment, we shall examine an alternative tool execution method using the sideload command, which will help us extend our tool capabilities beyond .NET. In the meantime, feel free to join our Discord channel to stay up to date with us, explore our courses, soon to be released labs, and one of the finest red teaming courses available. I've left a link to our group in the description below. Until then, stay safe and I will see you in the next one.